All right, math subject GRE practice test question number 28. I found this question pretty hard. Maybe I'm just not clever enough when it comes to integration, but for me, this one was a challenge. I mean, what we're being asked is to evaluate this integral from 0 to infinity of x squared e to the negative x squared. And that question on its own is really hard. In fact, I'm not even sure if it's possible using the methods of your typical Calc 2 class. I don't think the antiderivative of x squared e to the negative x squared exists. Or I guess more properly, I should say, the antiderivative of this function can't be written using elementary functions. So from the perspective of a Calc 2 student, you can't figure out this antiderivative, so you can't evaluate the integral. Fortunately, we're given some help. We're told that the improper integral from negative infinity to infinity of e to the negative x squared is the square root of pi, which is actually true. It's kind of a cool thing. This function, e to the negative x squared, is really interesting. It's a commonly used example in a Calc 2 class to really illustrate the fact that seemingly innocent-looking functions can be either really challenging or impossible to find the antiderivative of. You can find the derivative of whatever the hell you want. Give me an elementary function, its derivative is an elementary function, but that's definitely not true with antiderivatives. And e to the negative x squared is kind of a classical example of an elementary function that does not have an elementary antiderivative. So how are we going to use this fact to evaluate this integral? Well, really there's two issues going on here. The first one is kind of a little bit more minor. You might notice that the endpoints don't match up. But fortunately, that's easy to fix because each of these functions is an even function. As a reminder, all an even function is one that's symmetric over the y-axis. So f of x equals f of negative x, not to be confused with an odd function, where f of x is equal to the negative of f of negative x. This one's symmetric over the y-axis. This one's symmetric about the origin. And those symmetries can be exploited when you're evaluating definite integrals. If my definite integral goes from some negative value to the absolute value of that negative value, then this symmetry would tell me that the area to the right of the y-axis is the exact same as the area to the left of the y-axis. And this symmetry would tell me that the area to the right of the y-axis is the negative of the area to the left of the y-axis. In this case, the definite integral would be equal to 0. In this case, the definite integral would be equal to twice the area to the right of the y-axis. In other words, the area from 0 to the positive endpoint. What I'm saying is if f of x is even, the integral from negative c to c of f of x is just equal to 2 times the integral from 0 to c of f of x. Right? You've got to figure out the whole area. Just figure out the area on the right half and double it, because the symmetry means the area is the same on both sides. Anyways, we can take advantage of this fact to rewrite this given piece of information as saying that the integral from 0 to infinity of e to the negative x squared must be equal to exactly half of the square root of pi. What's nice now is that the bounds of my integrals match up, so it'll be easier to use this fact to evaluate this thing. So that's the small problem with solving this problem. The big problem with solving this problem is it's really hard to evaluate this thing, even with this little hint. And actually, I should be careful on how I worded that. It's really hard for me to evaluate this thing, even with this little hint. Maybe there's some clever solution. Maybe somebody will point it out in the comments. Maybe I'll have to make an addendum to this video to incorporate their comments. Who knows? The way that I was able to evaluate this integral is using integration by parts. Why integration by parts? Well, I kind of recognize that this e to the negative x squared is sort of part of this integral. So maybe if I can kind of break this integral up into parts, I might be able to use that fact. The most obvious way to break this up into parts is let one of the parts be equal to x squared and let the other part be equal to e to the negative x squared. And maybe you're like, which of these is u and which of these is dv? Well, I can't make this one dv because I don't know the antiderivative of this. So this would have to be u, and this would have to be equal to dv. But if you try going down that road, you kind of just get stuck. It doesn't help you any. Another choice for u and dv that might be a little bit more clever is to let one of those things be equal to x and let the other of those things be equal to x times e to the negative x squared power. First, convince yourself that the product of these two things is exactly the integrand here, and then make your decision on which one should be u and which one should be dv. Well, it'd be awesome if I could make this one u, right? Because the derivative of x is just equal to 1. So this gets significantly easier. The challenge with that is if I choose u over here, then I'm forced to choose dv over here, and figuring out v is challenging. However, it's not impossible. Unlike the antiderivative of this function, the antiderivative of this function is something we can figure out. That feels like something I should do off to the side here. I want the antiderivative of x e to the negative x squared. Well, maybe I could do a u substitution, right? I could let u be equal to, I don't know, negative x squared or positive x squared. It doesn't really matter. I'll choose negative x squared. With this choice, then du is negative 2x dx. In other words, negative 1/2 du is equal to x dx. Oh, that's cool because I have an x dx right here. This choice of substitutions allows me to rewrite this integral with the negative 1/2 out in front, e to the u du. I don't know that I have a favorite integral, but if I did, it would probably be this, because the antiderivative of e to the u is just e to the u. And now if I substitute back, since u is negative x squared, I get negative 1/2 e raised up to the negative x squared power, plus c if you want. Since this is the antiderivative of this is my choice for v, if this is my choice for dv. What I'm saying is I have a negative 1/2 e to the negative x squared up here. Two issues here. First one is, I don't think it's obvious that these should be your choices for u and dv. Asking somebody to see that this works under the pressure of the test is really asking a lot. The next comment is, I don't even think it's obvious that with these choices in the derivatives and antiderivatives that I've calculated, that we're going to be able to use this information to evaluate this integral. But anyways, plowing ahead, I'll use my integration by parts formula, which tells me that the integral of u dv is equal to uv minus the integral of v du. So if I plug in all my pieces here, I get that the integral of x times x e to the negative x squared, in other words, x squared e to the negative x squared, is equal to u times v, so maybe negative 1/2 x e to the negative x squared, minus the integral of v du. Well, du is just dx, so I could throw that out at the end. And then I could take this negative 1/2 and pull that in front of the integral symbol. So I'm subtracting negative 1/2. That's the same as adding 1/2. The integral of e to the negative x squared. If you haven't seen it already, here's where you get really happy. You're like, oh, I did it. The integral of e to the negative x squared. That's the information that was given in the problem. I'm not done, but I can at least see the light at the end of the tunnel. I want to integrate these things from 0 to infinity. So arbitrarily switching colors here for no real reason. I could say that that's equal to this expression evaluated from 0 to infinity plus 1/2 this integral from 0 to infinity. But again, recall, I love me some arrows going through the work, that this integral is the square root of pi divided by 2. So I'll answer the question by evaluating negative 1/2 x e to the negative x squared from 0 to infinity, and then adding to that 1/2 times this square root of pi over 2 value that was given to me. I still got some work to do over here, but whatever I get for this answer, I'll add that to the square root of pi over 4, and then I'll be done. However, at this stage, you might come and look up at your answers here, and notice that the square root of pi over 4 is one of the answers, and then notice that it's going to be really challenging to add something to the square root of pi over 4 and get any of these other 4 answers, where that something we're adding is going to come from this expression down here. Right, this expression isn't going to yield any square roots of pi. I bet this expression is going to end up evaluating to 0. I bet I'm safe in just calling this my answer. Doing that would be pretty damn lazy. Maybe not on the test, but definitely for a test prep video. So I'm going to go ahead and evaluate this thing. The first thing is your teacher would probably cringe at me writing things this way. Maybe what I should write is I'm evaluating negative 1/2 x e to the negative x squared power from 0 up to some number b. And really what I'm doing is I'm considering the limit as b approaches infinity of that expression. Okay, so let's see what happens. If I change all the x's into b's, I get the limit as b approaches infinity of negative 1/2 b e to the negative b squared power. Maybe I can rewrite that as negative b divided by 2e to the positive b squared power. Right, the negative exponent takes this factor and puts it down on the bottom. Kind of think about this, x is up on the top of the fraction. And then from that, I want to subtract, take this expression and change all the x's into zeros. What's that? Negative 1/2 times 0, e to the 0 squared, but 0 squared is just 0. E to the 0 is just 1. Negative 1/2 times 0 times 1. Sounds a lot like 0. So I get the limit as b approaches infinity of this mess plus 0 if you want. So I have the limit as b approaches infinity of this mess, negative b divided by 2e to the b squared power. How do I evaluate this thing? Well, the way I think about it is stare at it and hope you can just intuitively figure out what it's equal to. The top's going to get arbitrarily large negative, I suppose. What's going to happen down on the bottom? Well, an arbitrarily large number squared gets arbitrarily large, and e raised up to an arbitrarily large number gets arbitrarily large. I multiply it by 2. The point that I'm making is I'm going to have an arbitrarily large number divided by an arbitrarily large number. I have this infinity over infinity indeterminate type. To evaluate this limit, I want to use L'Hopital's rule. What L'Hopital's rule tells me is that this limit is equal to the limit as b approaches infinity of the quotient of the derivatives. The derivative of the negative of my variable is just negative 1. That's great. The derivative of the bottom, using the chain rule, I guess I'd get what? 2 times 2b, so 4b e to the b squared power. What's great about this form is it's no longer indeterminate. I can evaluate the limit just by looking at it. The bottom gets arbitrarily large, right? Infinity times even more infinity if you want. Negative 1 over infinity your teacher would probably cringe at me writing this too, is just equal to 0. What I'm saying is, sure enough, this entire thing just evaluates to 0. 0 plus the square root of pi over 4 is equal to the square root of pi over 4. The answer to the question, drum roll, sure enough, is just equal to A.